Arne Swinnen, and I'm going to talk about some vulnerabilities I found during bug bounty hunting in Instagram. So who am I? I'm Arne from Belgium. I'm 27 years old, and I've been an IT security consultant for a couple of years now. I work for Amviso, which is an IT security consultancy company in Belgium. And you probably don't know me, but if you have ever heard of me, it might be because of a talk I gave at Black Hat 2 years ago about antivirus detection evasion, or an event that I've been organizing the past 2 years now for my employer, which is called Cybersecurity Challenge Belgium. It's actually a CTF kind of game for Belgian students exclusively. Anyone who joined the CTF of OWASP today or yesterday? No one? Yeah, you might give it a go. It's fun. So, as I mentioned, the talk will be about vulnerabilities found during bug bounty hunting. I will first give an introduction about bug bounty hunting, my motivations, the goals, and also an introduction to the target that I chose, which is Instagram. Then I'll go through some technical hurdles that I had to overcome to effectively pen test this application and the mobile application. So man-in-the-middle and signature key phishing will be some parts that I will discuss. And then I'll go over the 10 vulnerabilities for which I've received a reward from Facebook up until now. So quite a lot of cover, and I'll conclude with a small conclusion and a Q&A questions. So, bug bounty hunting. Who in the room has ever bug bounty hunted before? Okay. Every conference, more and more hands get raised, so that's a good sign. Basically, what is bug bounty hunting? It's looking for vulnerabilities in production environments of companies. Facebook, Google have public bug bounty programs, and many companies are currently starting bug bounty programs on middleware programs such as HackerOne and Bugcrowd, or on their own website. Why did I get into it? Well, basically, I'm doing pen testing for a living, so I'm naturally interested in breaking things. And I also like to do capture the flag, and a bug bounty hunting event or bug bounty hunting is basically pen testing or capture the flagging, but for real. And you might get some profit out of it, so that's also a nice feature, of course. When did I do it? Well, actually, I'm working full-time, so I did it in my free time, in my leisure time. I started last April, or so April of last year, and I spent around more or less 6 weeks investigating Instagram, the target that I'm discussing today. So I sacrificed some of my vacations, but it was worth it. So Instagram, what do you need to know? Who of you has an Instagram account? Okay, not too many. Okay. Basically, I don't think it needs an introduction. It's Facebook for mobile pictures. It's getting more and more popular. And the reason that I chose it is because I didn't see too many write-ups of vulnerabilities that were found in Instagram before. So I figured, or it is very secure, or nobody has given it a proper look yet. And it was also included in Facebook Bugs Bounty program. What do you need to know about Instagram? Basically, it's a very simple application. You can upload pictures and you can share it with either the world if you have a public account, so the pictures are publicly available, or only with your friends that you have to allow if you have a private account. So that's the authorization model. It's extremely simple. So the technical setup, as I've promised you. Instagram, I didn't have an Instagram account myself. I never used it, so basically I didn't know any of the functionality. So I went ahead, I browsed to their homepage, and I wanted to register an account. But basically in the time, in April 2015, it told me you cannot register online. So you cannot register from a desktop. You really have to use the mobile application. This has changed now because since a couple of months ago, they also enabled registration on the desktop website, and I found a vulnerability in there, but that's for later. But thus, I had to get myself a test device and make myself an account on the Android application, because I do prefer Android. I have more experience with Android than iOS. So I went ahead, and of course, if you're penetration testing, you want to test most of the functionality. With Instagram, the bulk of the functionality is in the mobile applications. It's in the iOS application, in the Android application, and the web is mainly to view the pictures. But for example, you cannot upload a picture from a web browser from a desktop system. You really need the mobile application. So in order to decently pen test a mobile application, you need to be a man in the middle in order to have visibility into the requests and responses that are being sent by the mobile client and the server endpoint. So how do we usually proceed? The easiest way of all is to simply set up in your operating system configuration settings of Android a system-wide proxy and hope that your application is using it. Right, so here I imported my Burp Suite intercepting proxy certificate, set up my configuration, and started listening for requests. Unfortunately, Instagram is ignoring these settings. So my test, I first tested with a browser, and indeed I saw this request coming through. But if I tried to log in with Instagram, I didn't see the request coming through my intercepting proxy, but it did get through because it told me the password you entered is incorrect. So effectively, it's ignoring these settings, so I had to go a step further. So that was not a quick win. I had to go a step further, and basically what I did is, if the mobile application does not respect the configuration of the operating system, I have to enforce it. So I created an ad hoc Wi-Fi network with my local MacBook Pro, and I connected my test device on this ad hoc Wi-Fi network. So in this case, I am physically man in the middle, so there's no way for Instagram to not respect this. Of course, I still need internet on my MacBook Pro in order to allow the requests and responses to get sent and be received. So I sometimes just added a wire, so wired access to my MacBook Pro. But most of the time, I used my personal device with USB tethering in order to pass it on the internet. Because some of this testing was done during vacations next to the pool on holiday, and they don't tend to have wired access there. So that's why I went for the wireless access via the personal phone. And this effectively worked. So at the time, there was no SSL pinning implemented in Instagram. This has changed, but that's not the topic of today. So indeed, now I could see, I remade the login request, and now I could see the requests and responses to i.instagram.com, which is the endpoint domain of the mobile client of Instagram. So okay, that was the beginning. Now, zooming in on the login request, there was another problem. So this is the login request that I made, that I showed you before. And basically, it's a post request to API v1 account login. So far, so good, with only two post parameters. One is SIG-key version, and one is sign body. Now, the name already reveals it. Sign body is effectively containing all the parameters that I'm sending, that I've entered, so the username and the password, and even more. So you have 64 characters, then a dot, and then all the data that is actually being sent and being processed on the server side. So username ABC, password ABC, and some device identifiers specifically for this login view. Now, as you can imagine, the parameter is called sign body. If I try to modify any of these values, which is typically something you want to do as a penetration tester, you want to be able to fiddle with some variable, with some parameter values, I'm sorry. If I modified only one character, it told me your version of Instagram is out of date. So basically, the server is rejecting any requests that are not signed, because the 64 first characters here, it's actually an HMAC SHA-265 signature of the JSON array that is following here. So that was a hurdle that I, again, had to overcome. And this was a bit more difficult than the man in the middle. Basically, I had to fish the key that they were using to sign this array. So I could sign my own messages. Now, unfortunately, the key was not simply in a configuration file in the APK file. So I unzipped the APK file, I decompiled the classes.dex file in order to get to a Java-ish code. But unfortunately, it was not a hard-coded string there. It was actually being fetched from a native library, a compiled native library that was also included in the APK. And I finally got to the point where I could give a look at a function that was actually returning a password, so the key that's being used to calculate the HMAC. And unfortunately, it was also not statically inside the library. It was being calculated dynamically. So this is the routine that they are using, but they are doing some other calls to some other sub-methods. So this was rather hard. I figured maybe I should write a key generator for this. But what is also interesting is that this implementation changed every minor version of the Instagram Android application. So even a small update changed this key. So I would have to redo it all over again, and writing a key generator is not my core business, so it would have taken a lot of time. So I took a different approach. Instead of trying to figure out what the key is that is being calculated here, I decided to simply write a hook. You have a couple of hooking frameworks for Android. You have Cydia, you have Xposed, and last but not least, the new kid on the block is called Frida or Frida. I have actually no idea how to pronounce it. But with Frida, you can simply choose a native method. For example, here, Scrambler, which was the name of the library, the getStrings method. What I'm doing here is, okay, I'm attaching to the process, the Instagram process. I'm hooking this method, and on leave, so it's really an event handler callback, I'm just outputting the key to my terminal, right? So now, with this code, it's pretty easy. With every new version of Instagram, I hook this method. I trigger one calculation of a hash. So for example, I do another login request. The method gets called, and the key is spit out on my terminal on my MacBook. So that's a neat way to steal the key over and over again with every new version. That was a small success, but of course, just having the key does not solve the problem. I need to use the key to sign all outgoing requests that I've modified. And for that, I wrote a burp extender plugin. Basically, with the burp intercepting tool, I'm assuming Zap Proxy also has this functionality, you can write plugins. And I hooked into all outgoing requests. And I did some basic checks. Okay, does it contain the parameter sign body? If yes, let's recalculate the hash based on the key and hot patch this for all outgoing requests. And it effectively worked. And what was also handy is that with burpseed, you can hook into all outgoing requests, not only generated by yourself in the repeater module, for example, but literally all outgoing requests generated by the proxy, the repeater, the intruder, the scanner. This also allowed me to find some vulnerabilities up next. So finally, I arrived here. I could start pen testing, and this took me around 2 weeks, because I was not very familiar with hooking on Android, so I had to teach myself, and even the man in the middle setup with the MacBook in between was new for me. So this took me 2 weeks, and I didn't pen test anything yet. I hadn't found anything. So now I was quite eager to start. So the vulnerabilities that I found, we've got 10, so buckle up. First one was actually not on the mobile application, ironically, but it was simply on the landing page of Instagram.com, which surprised me a bit. So here we have Instagram.com, and it's presenting me the Dutch landing page because my operating system where I was testing on has the Dutch language as default. Now, you also have a language picker on the left bottom of the page, which is hidden here. If you, for example, select English there, it would append the get parameter HL with the value EN. So we see that quite often, HL for home language, I believe that it stands. So okay, I figured, typically when I see this case, I figure perhaps this value is used in a calculation of a language path. So typically to test for path injection, I add ./ because this is legitimate in a path string. And effectively, this still served me the English web page, which is not the default one for my case. The default one is in Dutch. So this value is effectively accepted as being an identifier for English. This does not confirm the vulnerability yet. So I went ahead and tried to fetch another file. So by going up a couple of directories and trying to read etc password, appended with a null byte to null out anything that is appended on the server side to this value. But unfortunately, the response said, oops, an error occurred. So it's not effectively rejecting this value, but it cannot serve me a decent response. So this, I was a bit stuck here. And after a while, I decided to look into the documentation of Django, because Instagram is written in Django from Python, in Python. And yeah, you can learn about it on their engineering blog, which is really a treasure trove when you're bug bounty hunting. First, check out the engineering blog of the company. They usually give some hints about the technologies they are using, and that proved to be very interesting here, very useful. So here you can see a reference to language files in Django, Django conf locale, and then a language code, a dynamic language code, lc messages django.bo, which is a language file extension. So I figured, okay, maybe if this is effectively where my value is being inserted in, I can go up one directory and test whether this is effectively the locale directory. So I tried this with this following value, hl equals ... /locale/en, which should be the same as simply en. And as you can see, again, the language, the English landing page was served. So hereby confirming that I have an actual path traversal or path injection vulnerability found on the landing page. Now, what can you do with it? That's something different. First of all, what I could do is read, for example, /dev/urandom. This is on Linux a file. Well, it's not a file, but it keeps on giving you random string, continuous flow of random characters. So that could result in application denial of service. And also what I found out is, yeah, of course, in order to completely confirm it, I replaced locale with an unexisting directory, and it served me the Dutch page, so that confirmed it completely. And what I did also is I tried to brute force directory names from other directories. So I learned about locale from the documentation. So I started to brute force some others. I picked a word list of popular directory names from the FuzzDB project, which might be known to some of you. And I got not less than 42 hits. So I found out a couple of sensitive names that I had to redact in this presentation, a couple of sensitive directory names in the same directory where the locale directory was located. And essentially, this vulnerability would also allow me to brute force all directories on the production server of www.instagram.com. So that was my first success. So I reported it to them, and I was quite happy because I found a vulnerability. And unfortunately, they responded to me, although this issue does not qualify as part of our bug bounty program, we appreciate your report. So that was kind of a bummer, right? Because I could effectively bring down a lot of servers from them just by feeding /dev/urandom. I could brute force, for example, the home users, so the users on their Linux system by brute forcing the home directory. So that seemed to me like an issue. So I elaborated a bit, and then they came around and told me, that response was intended for a completely other report, so yours is valid, and here's $500. So at the time, this was better. But still, if you think about it, $500 is their minimum bounty amount. It's not very high for something that could have brought down that could have majorly affected their availability. But left aside, I was still very happy. Second vulnerability, also still not on the mobile application space. Actually, maybe even simpler. So if you register a new account, in this case, victim 14 April, on the 14th of April, I tried this attack. It sends you a mail to confirm your email address. Very typical. And if you click the link, it takes you to the following URL, instagram.com account confirm email, a user identifier, and then a base64 encoded value, which is effectively holding your email address. So if you base64 decode this, it was instagrampentestuser@gmail.com in this case. So I had to visit this link, and in order to activate or confirm my email address, I had to log in with the account to which this new email address was linked. Now, I didn't do that. I just logged in with another Instagram account and see what the message was. And it effectively detected that this was not the correct account, and it told me, no, you're logged in as attacker 14 April, but you have to log in as victim 14 April. So you're not, it's actually leaking the username that is attached to an email address. And that's not allowed because email addresses are guaranteed to be private data on Instagram, according to their documentation. So this was a vulnerability, but I always like to offer a decent proof of concept. So I went ahead and base64 encoded the email address mark.zuckerberg@facebook.com. And effectively, it told me, no, that's not correct. You have to log in with username the Mark Zuckerberg on Instagram. So basically, it's an oracle allowing me to guess email addresses, and it tells me the username, which is not a very big deal, but maybe in censored environments where internet is monitored, for activists, this might be a deal. So I went ahead, I reported it to them, and this was a better outcome. They fixed it in like 1.5 days, and they donated $750 for this very simple vulnerability. So that was a good success. Now, the third vulnerability I can unfortunately not disclose at this moment because it's still not fixed by Facebook. I reported this, ironically, on 9/11 of last year. And I already received a bounty for this one in February because they told me it's taking us more time than expected, but you already get your bounty now. And I asked them a couple of weeks ago whether it's already fixed, and I can disclose it here, but unfortunately they're still working on it. So this also shows that you sometimes, as a bug bounty hunter, you have to have a lot of patience as well from your side. So I will certainly disclose this vulnerability as well later, probably on my blog or another presentation, but not for now. Fourth vulnerability is finally in the mobile application. Instagram, it's all about pictures, right? So I tried to use this functionality and I uploaded a picture. And the response of the upload request was the following. Basically a lot of gibberish, and I highlighted the interesting parts. First of all, your uploaded image gets an ID, a very long one. It's not a UUID, but it comes close. It's hard to brute force. And the ID is actually used internally to refer to the image. So this is the real unique identifier. But it also gets a code, which is also unique to the image. But the code is not really being used internally. It's actually being used in the path of the link on the main website to this picture. So you see -E1 and 10 characters in total. And if you browse to instagram.com/p/the code, if you're allowed to view the picture, you would see the picture. Now, I did the test with a private account, so I uploaded a picture with a private account, and I then went to this URL unauthenticated, and as expected, you cannot see the picture. Now, if the private account is logged in, so the owner of the picture is logged in, he or she can see the picture. So far, so good. Now, there is one piece of functionality in the mobile application that allows to modify the access control around this picture. So you can, on a picture of your own, you can select copy share URL. And basically, it will send the following GET request, so API v1 media, your picture ID of your proper own picture, /permalink, and it would reply the permalink that we actually already knew about. But now the access control around this picture has changed. Now it has become widely available to everyone. And why does this functionality exist? I'm assuming that Instagram made this functionality in order for their users to be able to share pictures with users who don't have an Instagram account. So basically, they're allowing to give you a URL to the picture, and you can visit it without a decent Instagram account. So now, the whole world can view this picture from a private account, although the private account will probably only share it with a couple of friends, with the people he or she wants to share it with. And at this point, I figured out, okay, actually the only thing that withholds me as an attacker to discover all these private account pictures that have been deliberately shared by the owner with a couple of people is the entropy of this token here. So the code that was generated previously, 10 characters. Now the alphabet of each character is 64 characters, so it's a lot of possibilities. It's hard to brute force. But I started to investigate, and I found some patterns. So the first pattern that I found was every Instagram account has a unique user ID, and it's an incremental ID. So for example, the founders, Kevin and Mikey, they have ID 3 and 4. And I just, these are public accounts, so I can view all the permalinks of their pictures. And I noticed that the 7th and 8th character of the code of their permalink pictures are almost the same. The 7th character is always the same. No, the 8th character is always the same. It's a B, as you can see. And the 7th character is either a G or an A. Now, this was the case for user accounts or accounts with a user ID which were close to each other. I also did a test with Britney Spears and a random account that was very close to her user ID. And it were different characters, as you can see, but the pattern remained. So as an attacker, that's interesting information, because if I have a private account, I know the UUID of a private account, that's public information. I can just search for some public accounts near this unique ID, and I can discover 2 of the 10 characters that are needed for these URLs. That's already something, but that's not enough. That still leaves 64 to the 8, which is a lot of possibilities. So I had to go a step further, and I implemented a small Python script which basically monitors a private account, a public profile page, and the public profile page of a private account, it does not show any pictures, but it shows how many pictures have been posted by this account. So basically, this Python script is monitoring the number of posts or number of pictures that have been uploaded by this private account. And once it increments, it will immediately upload a picture as well, but with an attacker account. Right? So completely different Instagram account, it would upload a picture. And then I gathered some samples with 2 test accounts, obviously. And I listed the codes that were generated for both pictures. And effectively, this proved to me that the first 6 characters of the code are actually based on time. And with this Python script, with this monitor script, which is pretty fast at uploading a new picture, I could steadily detect the first 4 characters, which reduces the entropy enormously. Because if we do the math now, we have 4 well-known characters. The 7th and the 8th we can already predict, so that only leaves 4. So 64 possibilities per character to the 4th times 2, because remember the 8th character can be of 2 values. It gives you 33 million possibilities, which is easy to brute force nowadays with a simple brute force tool. Trying to fetch 33 million URLs, it only takes a couple of hours with the performance, at least with the server who has a good uplink. So I could essentially, as an attacker, start brute forcing URLs of a private account and land on picture that they have, private picture for which they have generated this permalink. So it's a long fetch, but I finally ended there. And Facebook went along and they acknowledged and fixed this by making the code a lot longer. And they gave me $1,000 US. Okay, now maybe anyone noticed in the previous vulnerability, if you select copy share URL, the underlying mobile application, so the Instagram application, is generating a GET request to the server. But basically, this should not have been a GET request because it's a stateful action. This request changes the access control around this permalink, this picture on this URL. And what's even worse is post requests to the API endpoint are properly protected against CSRF, but GET requests are not. Tom van Goetem talked about this in the previous presentation as well. So typically, CSRF is only being used to protect post requests. And here we have a GET request. So this allows me, as an attacker, if I can lure an authenticated victim, Instagram account victim, to my website, I can make this request on their behalf, and I can share their pictures on their behalf without them knowing. So if it's a private account, I can make their pictures public, which is a big deal. Now, in order to successfully execute the CSRF, I still needed 2 informations. First of all, I needed the image ID of a private picture of my victim, which is not public information. Of course, they are not visible, so you cannot fetch this information. And with CSRF, you cannot read the response, so I also had to have a way to predict the final permalink of this picture. As you can see, the token grew a lot longer, but still the CSRF vulnerability was still there. So I had to use some leakage vulnerabilities. First of all, I found a way to discover image IDs of private account pictures, simply with a simple insecure direct object references in an endpoint that allows me to fetch the new pictures in which I have been tagged. So if the victim was tagged in a new picture, he made a picture and he tagged a couple of people, among which himself or herself, I could essentially fetch the image ID. So that was already one part of the problem. The second one that allowed me to discover the permalinks was, again, in the same endpoint here, in the permalink endpoint. I could simply exchange the image ID of myself, or a picture of myself, with the image ID that I now discovered, and it would return to me the URL. It would not modify the access control around it, because that would have been a very nice case, but it would leak the URL. So, complicated CSRF attack. Facebook acknowledged they fixed it, they made it a post request, and they also rewarded $1,000. So we're halfway, and now, as you might have noticed, the bounties keep on rising, so now the very interesting ones start coming. Here, is a case of, let me explain. So if you have an Instagram account and you want to change your password, you have to supply your old password. It's best practice, it's common practice. Now, if you want to change your email address, which can be used to reset your password, you didn't have to supply your current password. This was actually a bypass around this, I thought. So I went ahead and I changed the email address. And to the new email address that I entered, I got the same confirmation email to confirm it. But there was also an email sent to the old email address saying, hey, somebody has changed your email address. Was it not you? In case it was not you, click here to secure your account again. And basically, this here gave you the option to reset your password again, so to reclaim your account in case someone else changed your email address. So this is their protection against this scenario, which is a bit odd. I advise them to just ask for the password when changing the email address, but it's a way. Now, the attack scenario that I came up here for this case was, imagine that an attacker has temporary access to an authenticated session of a victim. For example, through SSL pinning, which was still possible until the end of last year, through a cross-site scripting vulnerability, through physical access to an unlocked phone, for example, when somebody is visiting the bathroom in the pub. And the attacker has like a couple of seconds to fiddle on an authenticated session. What he could do then is change the email address of the victim not once, but twice. Right? He would change it to first email address under his control and then a second one, which would, and then he would proceed with the reset password scenario. Now, in this case, the attacker has control of the account, but the victim still has a reclaim back link. But the attacker also has one, and you see where this is going. So in this case, the victim would utilize his link, or her link, to reclaim back the account. And here was the vulnerability. The reclaim link that was sent to the first email address of the attacker was still working. So finally, the attacker could use this link and completely overtake the account. And there's no way that Instagram is explaining in their documentation to get this account back. So it's an account takeover based on temporary access to a victim's account. And surprisingly enough, they reward this quite generously because it's some prerequisite, but they gave $2,000 for this one. Okay, up next is something completely different. It was about stealing money from Instagram. In Instagram, you can link a phone number, so a mobile phone number, to your account. And the registration process goes as follows. You enter the mobile number, they send you a code, you have to enter it, and then you're linked. Right? But if you don't enter the code after 3 minutes, they will call you, or at least that's what they say in the application. So I figured out, okay, let's play the waiting game. Let's see if they call me. And effectively, they were calling me. So they were calling from California to Belgium, which is quite an expensive call for them. But they were calling me, and they were effectively, I don't have sound here today, but it's basically saying your code for Instagram is 1, 2, 3, 4, 5, 6, but in a very computerized voice. So the attack scenario that I came up here is, let's not enter my own test device's phone number, but let's enter a premium number and see if they call this number, which is a valid attack scenario in my opinion. So I looked around on the internet for providers of premium numbers, and there's a lot of scams there, so you have to look out. But I finally found Eurocall24.com, which allowed you to pick a whole bunch of premium numbers. And I went ahead, I registered one in United Kingdom. I entered it on the mobile application, and I watched on their live incoming calls dashboard that effectively I received a call from the same number in California to this premium number. So at this point, Instagram was giving me money. And it was getting better because I could not make one call, I could make multiple calls. There was some rate limiting protection. I only could make one call every 30 seconds, but it was unlimited per account. So I could just easily make a nice loop, and I could keep on calling my own premium number. So I did a proof of concept to call 60 times, and with a throttle of 30 seconds in between. And this ended up with £1. Yeah, it's a UK website. So £1 was earned. So this is the point where I thought, okay, this proof of concept is good enough. I will send it to them. And I got the following response. This is intentional behavior in our product. We do not consider it a security vulnerability, but do have controls in place to monitor and mitigate abuse. Which was not very, it was not what I expected. I was actually quite disappointed. But then it came to me, this is intentional behavior in our product? This is actually even better than just a small bounty. I have black and white that this is intentional, so I can make a living out of this, right? So I had a moral dilemma, but I decided to contact them again and tell them, okay, the proof of concept, indeed, I cannot steal a big load of money because I only used one account, but I can easily create 100 accounts, set up 100 loops, and steal more than $140,000 a month. And at this point, they came round and they acknowledged, yes, now we're talking. And they gave me $2,000 eventually. So that's a completely another kind of attack scenario. 8th vulnerability is actually the most simple one I've found. Basically, what I do with every new version of Instagram, mobile Android application of Instagram, I decompile it to the Java-ish code and I extract the strings. And basically, I do this to identify new endpoints that are in the code. And I stumbled upon discover/SU refill, a new endpoint, and I tried to trigger it by using the mobile application, but it was never making a request to this endpoint. So I had a new endpoint, but I didn't know how to speak to it. So I dived into the obfuscated decompiled Java code, and here you can see discover/SU refill was the endpoint that was in this class. And it also leaked some information about parameters that it was expecting. Target ID was an interesting one because IDs are always interesting for insecure direct object references. So I went ahead and I forged a request in the repeater tool based on an existing request. And I sent a cookie from an attacker Instagram account and a target ID from a victim test account. So there was no relationship between these two accounts, and this one was a private one. So actually, I could not fetch or normally see a lot of information of this one. And the response, luckily, it showed some decent information. Basically, it is returning the users that this victim account, so the target ID values account, is following, which is considered private information. And Facebook rewarded. They also fixed this like in an hour, because it's simply an access control check that they have to add. And they gave $2,500 for like 5 minutes of work. So that was very nice. 9th vulnerability, this one I've also posted on my blog, so maybe it's known to some of you. I mainly did testing in 2015, and then I stopped for a couple of months with Christmas and holidays. And in February, I tried to log into my account again, and it told me, you've been quite inactive for a couple of months, so maybe we need to reactivate you. We want to check for sure that it is you that is logging in. So I could verify by email. Now, the interesting case here is already highlighted. My unique user ID, which is, remember, incremental, is in the URL. So as a pen tester, obviously, you want to try another user ID there and see what you get. And I started to enumerate 1 million user IDs which were close to mine. And I stumbled upon some interesting results. So most of the pages gave a 404. But some gave the following screen, so also a reactivation of the lookout, but through a CAPTCHA. Only 0.1% of the 1 million accounts, though. 0.2% gave me the screen that I received, so to verify your account again by SMS or email, but still, it's not very interesting for an attacker, because this is the profile picture that is already public, so it's not very interesting. Up next was more interesting. 0.17% of the 1 million accounts, they allowed me on this screen to update the email address, which is, remember, it allows me to overtake the account through the reset password. That was already nice, but 0.17% is not a lot. And luckily for me, I also landed on almost 4% of screens that allow me to update the phone number. And just like with the email address, you can also reset the password of an account if it has a linked phone number. And even better, for some, it also showed the previous phone number, so it's clearly a leakage of private information. And this escalated, I escalated this quickly to Facebook, and I believe they fixed it in 12 hours or something. And they donated me $5,000, which was very nice because I didn't test for a couple of months. I landed on a lookout page, and suddenly I received $5,000. So thumbs up for Lookout. Last but not least, final vulnerability is about authentication credentials brute force. Basically, Instagram, as I've told you, the usernames are public, and they are enumerable because their UUIDs, they are incremental. So basically, an attacker can easily build a list of all the usernames of Instagram. And it's the username that you need to use to log in. It's not the email address. So usernames are known. They have a very weak password policy, so it allowed passwords like password, which is very common, 1, 2, 3, 4, 5, 6. It was also allowed. And they don't have two-factor authentication. So it's a good target for testing credential brute forcing, because with a nice list of password dictionaries, you could compromise a lot of accounts. And this is where my plugin really proved himself, my burp extender plugin really proved himself. Here you can see an account an account brute force attack on the mobile authentication endpoint. So literally entering credentials and replaying this in Burp Intruder. And as you can see, until the attempt number 1000, it would tell me whether the password that I guessed is right or wrong. But from that moment on, it would tell me, no, the username you entered doesn't appear to belong to an account. While obviously the username is static in this loop. So obviously the account is still existing. This is simple rate limitation protection. So if I made the same attack from another IP address, I could again make 1,000 requests. So okay, they had some protection, but I left this running for a while, and on number 2000, so after attempt number 2000, it started differentiating between the username you entered doesn't appear to belong to an account and a valid response saying the password you entered is incorrect or correct. I have no clue who implemented this and why this was wrong, but basically the rate limitation protection was nullified after 2000 attempts. The only downside is I had to make 2 requests for 1 answer, but it's easily scriptable, so I went ahead and scripted this, and this allowed me to very quickly discover the password of an account. So that was the first one. Actually, I found a second one, and I promised you it was in the registration on the desktop website, so the main website of Instagram. And here, if you register an account, it would send the following request to accounts web create Ajax. And I decided to replay this account and to also remove everything except the email and the password, because the rest is added by JavaScript. And if I replayed this request with the password that I registered with, it would tell me those credentials belong to an active Instagram account. But if I would replay this request with another password, so wrong password, it would tell me, email required exception. So basically, it's an oracle that can be used to verify whether my password guess is right or wrong, and there was no rate limitation on this one, not even after 1,000 or 2,000 or 5,000 attempts. So I reported these separately. Yeah, I also did a proof of concept. The guess number 10,001 still revealed that the password was correct, so this confirmed the vulnerability. And Facebook also fixed these vulnerabilities and paid out $5,000. So that's it for now. To conclude, in total, Facebook gave me $20,500, which is a nice payout. But of course, I had to do my best for that. And actually, they donated a bit more money because the first $5,000 that I earned, I gave to a charity, and they double it. So in total, they gave almost $25,000, and the charity was also very happy. So that was nice. And maybe some advice for those who are already bug bounty hunting or wanting to get into it. If you are hunting for bugs, keep calm and try harder. You sometimes really have to go a step further than typically to find something. If you're reporting, be patient. I'm still waiting for some reports which are months and months old, but patience is a virtue. And if you're disclosing, be responsible. So don't disclose anything that isn't fixed yet, because you will ruin the relationship with the company as well. thank you for your attention, and I'd be happy to take any questions you have. Well, I mentioned HackerOne and BugCrowd in the beginning of my talk. These are actually platforms where a lot of companies can register themselves, and yeah, they post the scope of their bug bounty program. And researchers can also make an account, and you can send reports in a decent fashion to them, and they get triaged. So this would be what I would advise. You have a lot of programs there. What I did, I first started with smaller companies just to get the feeling, and then I mainly chose Instagram because I didn't see too many write-ups. So you have a number of, at the time, 1 year ago, you only had the big ones, but these days you literally have, for example, Tesla, for example, Slack, they have a bug bounty program, so there's a lot of choice, actually. Yes, please.
You had the third not making bigger discount.
Mm-hmm.
That one is now almost 10 months old.
Mm-hmm.
So have you set for yourself a time limit? Trying to say if they haven't disclosed by then, I'm going to play, or?
It's a good question. And sorry? Yes, indeed. So the question is the vulnerability where I'm waiting for the fix for more than 10 months. Have I set for myself a date that I will responsibly disclose anyway, for example, through a blog post? Well, I have been in doubt about that, honestly. But on the other hand, some issues are easier to fix than others. And this particular one does not have an easy fix with one liner of code. So I understand that this takes more time. But of course, if it takes 10 years, I will not wait. But I haven't set a fixed date personally for myself yet. But it's a common problem with bug bounty hunting. Sometimes you have to wait for a long time, and it can be frustrating indeed. Any other questions? Yes, please.
For example, in the course of like, face any defensive mechanism for the exam, for example, where you block at some time, or you just throw as many questions?
Well, in the mobile application, indeed, the question was, did I face any additional protections or any lockout mechanisms from Instagram on the brute force attack? Well, it is true that if you don't use an account for a couple of months, they ask you to re-verify your email address. But if I brute force the password of an active account and then logged in through an IP address in Hong Kong or China, it just let me in. So there was no location-based anomaly detection or anything. I didn't hit any protection besides the rate limitation based on IP address.
So based on how much they rewarded you for different vulnerabilities, do you agree with kind of the severity of the fine that was found, or do you think kind of, oh, this is really nothing too much for customers?
Okay, good question, thank you. So the question is, do I agree with the payout, the rewards that they have given me for each vulnerability? The logical answer, not always. I think some vulnerabilities deserve a higher reward, relatively. I think some were generously rewarded. But at the end, it's at their discretion. I cannot influence it, or hardly. So that's the life of a bug bounty hunter. You have to comply with their decision. But as I mentioned, for example, the first one that allowed me to bring down a lot of main servers, I believe this might have yielded a higher payout, for example. But in the end, that's a bit part of the game if you're bug bounty hunting.
A follow-up question. Any advice that you would give to bug bounties in terms of the write-up when you disclose?
So indeed, advice if you disclose for a write-up. Well, I typically ask the company first. I make a draft on my blog. I give it to them for them to have a proofread. So I try to have their buy-in for my write-up before publishing. Sometimes I do give a hint or two about the reward or give some comment on it. And if you give them the opportunity to validate, then you won't have any problem. That's at least my reasoning. That's what I did.
I guess my question was the write-up that you sent initially.
Oh, I'm sorry. Yeah, so the question was not the write-up that I publish afterwards, but the report that I submit. Well, I always try to submit a real proof of concept, because bug bounty programs, they receive a lot of submissions which are vague and not really a proof of concept, which are theoretical vulnerabilities. And I do know that this is more a burden on their end and it will never get accepted. So I first try to make a decent proof of concept and then send this over, so to minimize the number of rejected reports. So that's indeed a good advice I can share.
Okay, let's thank Arne again.
Thank you for your attention.